Well, my dear participants, I shall continue on normal distribution. So, note that the area between minus 1.96 to 1.96 is 0.95. How we can compute this area? This is nothing but P norm 1.96 minus P norm minus 1.96, and the area under the curve, normal curve, it is 0.95. See, what should be the value of P norm? Area under the standard normal curve below 0 is nothing but it is 50%. So, P norm 0 is 0.5. Similarly, an example of Q norm 0.5, that is the quantile when area under the curve is 0.5. So, Q norm should be, actually it should be 0, because Q norm quantile is the inverse image of CDF. But Q norm 0.975 is nothing but 1.96. 1.9. So, these are the properties of normal distribution. Similarly, quantile corresponding 0.025 is minus 1.96. So, Q norm 0.9756 is plus 1.96 and Q norm 0.05 is minus 1.96. An example of 10 random simulations from normal 0, 1. Suppose if height is equal to normal, height follows normal distribution with mean height 168 plus minus, that is SD is 5 centimeter. Then we can simulate these 1000 heights using R norm, random simulation from normal distribution. So, 1000 observations are being simulated. 1000 observations are being simulated, and mean is 168 centimeter. Mean height is 168 centimeter, and SD is equal to 5 centimeter. So, we can simulate these and we can look into the height simulated, HEIGST, height. These are the simulated heights, and these are the 1000 heights which are being simulated. Suppose we want to compare the probability of height less than 6. So, what we have to do? We have to use P norm, probability less than 1.158, mean is equal to 168 and SD is equal to 5. So, it is 0.022. But if we want to compute probability less than 168, so it is 0.5, because 168 is the mean or median. Suppose we want to compute probability of height greater than 170 centimeter. So, what we have to do? P norm 170 and mean is 168. Mean is 168, SD is 5, and lower dot tail is equal to false. Actually, by default, it is lower dot tail is equal to true. So, it computes area less than 170. But since we want area greater than 170, we have to give the additional argument lower dot tail is equal to false, and this is the point. Area under the normal curve greater than 170 is 0.345. Probability of height between 166 to 170. So, we can compute this area, probability of height less than 170 with mean 168, SD 5 minus probability 166. So this is the area between 166 to 170, and this is the probability 0.31084. Values of likelihood, and these are the log likelihood, values of log likelihood. So here LL1 is equal to d norm, value of the density, and then height is the vector, and mean is equal to 168, SD is equal to 5, log is equal to true. So log is equal to true, it will compute log likelihood, and this is the vector of log likelihood. Now if we get a sum of log likelihood, so this is the sum minus 3025.517. Suppose y bar is equal to mean height, SD height is equal to SD height, and if we are computing log likelihood with estimated mean y bar and SD height, log is equal to true. So here it is, this can be organized in the form of a table. See, this is C exact is equal to sum LL1, estimated is equal to sum LL2. So this is the exact likelihood is minus, that is likelihood at mean is equal to 168 and SD is equal to 5. The likelihood is minus 3025.517 and estimated is minus 3025.50. So this is the estimated likelihood. So these were the features which we were talking about. The fact is that maximum likelihood estimation, we try to get those values of the parameters which return maximum value of the log likelihood. Shape of the distribution with different values of SD. What will be the effect of the shape? Say for example, curve d norm x, mean is equal to 0, SD is equal to 1, from is equal to minus 3 to is equal to 3. Then on the same curve we want curve d norm x, mean is equal to 0, SD is equal to 2. So here SD is equal to not 1, it is 2. SD is equal to 2. And then add is equal to true, because this will generate a new plot and we want to add a curve with SD is equal to 2 on the same plot. So we have to write here add is equal to true, and line type here will be LTY is equal to 1, that is solid line, and LTY2 is equal to, this is the dashed line, and then another curve with SD is equal to 10, SD is equal to 10, and that is nothing but with very high SD, what will be the shape of the distribution, and legend top left stands for top left position, legend should be there, and then legend, what will be in the legend, SD is equal to 1, SD is equal to 2, SD is equal to 10, and line type is equal to first solid line, second dash line, and third is also a dash line with smaller dashes. So if we run this whole chunk, we will have a plot like this. So this is the output. Solid line is normal 0 with SD1. So this is the solid line, and then dash line with SD is equal to 2. This is the dash line, LTY is equal to 2. And then for SD is equal to 10, it becomes almost flat. It becomes almost flat. So as we are increasing SD, this distribution, shape of the distribution become flatter and flatter, flatter and flatter. From figure, above figure, we find that as SD increases, shape approaches to uniform distribution. So this is all about normal distribution. Now I am going to talk about another distribution which is known as uniform distribution. Uniform distribution is also one among the important distributions, R unif. See, y is equal to R unif. When we were generating sample from normal distribution, it was R norm. Since we want to simulate observations from uniform distribution, it is R unif. N is equal to 1000, min is equal to 0 and max. So it will simulate 1000 observations between 0 and 1. So these are the simulated observations which are between 0 and 1. So these are the 1000 observations between 0 and 1. If we want to compute mean of this, it is a well-known theoretical result that mean of y should be 0.5. Exact value is 0.5. Now what this approximates? This is on the basis of simulated data. So here it is 0.4879. Similarly, where variance of y, it is a theoretical result that it should be 1 by 12. For uniform 0, 1, it should be 1 by 12. So where y is equal to 1 by 12. So if we want to compute 1 by 12, it is 0.0833. So this is the exact value 0.0833, and on the basis of simulation we are getting 0.084. So they are very close, they are in very close agreement. Now if we want a histogram on the basis of simulated data, so here hist y prob is equal to true, and then we are adding a curve d unif. This is the curve d unif x. From is equal to 0, 2 is equal to 1, add is equal to true. So if we run this command, see what kind of graphics we are getting. See, this is the, so this histogram has been made on simulated data, and this is the exact curve. This is the exact curve. So both are matching, and that means our simulation is correct. Represents uniform distribution. More examples on uniform 150 to 180. Y is equal to R unif, 500 observations between min is equal to 150 and max is equal to 180. If we want to make a histogram, it will be hist y prob is equal to true, and then we want to add a curve d unif x, add is equal to true. See, here it is not showing because I have not given the range of the curve, parameter of the curve d unif, and that is min is equal to 150 and max is equal to 180. So now if we will run this, we are getting the histogram. So histogram and curve both are matching, so that means our simulation is correct. See, then I am going to talk about exponential distribution. See, exponential distribution like normal, we can also define exponential distribution. So, instead of d norm, we have dexp x and rate value of the density. Then pexp q rate parameter value of the CDF. Then qexp p rate value of the quantile, and rexp and rate random simulation from exponential distribution. So, this logic works. Say for example here RE is an object and REXP, that means random simulation. How many simulations? 10,000 simulation with rate is equal to 1. So, it will generate 10,000 values from exponential distribution. And it is a well known result that for rate is equal to 1, the mean of this distribution should be 1. So, it is 1.00, and SD should also be equal to 1. So, SD is also 1. So, that means our simulation is correct. Now, what will be the probability of random value RE greater than 3? So, what is the area under exponential curve greater than 3, and that is probability. So, actually this we can compute using the command PEXP, and the point is 3, and then rate is equal to 1, and lower dot tail is equal to false. Lower dot tail is equal to false. So, this is the value 0.049, but this we are using PEXP, a function, standard function, but the same thing we can compute by simulation also, and that is nothing but here mean, because actually to compute mean RE greater than 3, it returns logical values. So, if R is greater than 3, it returns true, otherwise false. So, and these are the 1000 observations. So, that means if we take mean of these, it will be trues divided by the total. So, mean of RE greater than 3. So, this is nothing but probability. It is 0.052, whereas PEXP it is 0.049. So, exact value is 0.04978, and on the basis of simulation it comes out 0.0526. So, both are in close agreement. So, that means our simulation is correct. Now, histogram of the simulated data RE prob is equal to true, and curve DEXP, then curve DEXP rate is equal to 1, add is equal to true, LWD line width should be 2. So, when we run this, we are getting this curve. So, this histogram is made on simulated data, and this curve is exact exponential density plot. Since histogram is made from simulated data and curve is exact, but both are matching, This implies that our simulation is correct. The whole story is depicted in the figure, in this figure. The whole story is depicted in this figure. Now, I shall talk about gamma distribution. So, gamma distribution is also a very important distribution. Gamma is an important model for studying reliability data. It has a relation with exponential distribution also, because for exponential distribution, if shape is equal to 1, it returns to exponential distribution. So, here y is equal to r gamma, 1000 observations are being simulated from gamma distribution with shape is equal to 1.2 and rate is equal to 0.02. And then these are the simulated 1000 values, control 2, and these are the simulated 1000 values from gamma distribution. Gamma with shape is equal to 1.2 and rate is equal to 0.02. If we want to compute mean of, so exact mean should be 1.2, that is shaped by rate. So that should come out 1 point mean 1 is equal to, see, mean of gamma, it should be 1.2 divided by 0.02. Mean 1. So this is 60, mean is 60. Mean of gamma distribution is 60. And see, this is the exact value 60. But what you get by simulation? Mean of y, it is 59.16. So this exact result is very close to the simulated result. It is 1 by this thing. Suppose we want variance. So variance of y is what? Variance of y is 2801.76. So this variance is based on simulated data, whereas exact variance is nothing but 1.2 divided by 0.02 raised power 2. So this is 2801, and on the basis, this is the exact value, 3000 is the exact value, and on the basis of simulated data we are having 2802. But these things can be improved if we get more number of simulations. Say for example, instead of 1000, suppose we are simulating 10,000 variables. Then see what happens about variance. Variance is 2923. So it is very close to 3000. So that way. Now histogram, prob is equal to y, prob is equal to true, and curve d gamma, we are plotting a curve d gamma, shape is equal to 1.2 and rate is equal to 0.02, add is equal to true. So if we run this chunk, we can run this chunk. See, this is the, this histogram is made on simulated data, whereas this curve is the exact curve. So here it is being cut on the neck. So how we can adjust this? Here the limit is 0.008. So if we put here limit y lim is equal to C 0 point 1 0.001 0.01 0.01. Now see what happens, because earlier we were having this thing cut. Now we want to make it safe. So we run, when we run, see, still 0.009 and see what happens. 0.009, still it is cutting. So 0.018. Now see what we get. Now it is safe. So we can make y lim adjustment, and we can get this is within the range. Now it is not being cut on the neck. So this adjustment can be made when you are graphing. Figure represents the histogram on the basis of simulated data overlaid by exact curve. More examples on gamma distribution. Which we shall talk just in our next video. More examples on gamma distribution, then different shape of gamma, and then beta distribution. So these things we shall talk in our next lecture. More examples of gamma distribution.